Hello, everybody. So like Alex said, we work together at Bazaar Voice. I've been at Bazaar Voice for 4 years now, and that's been long enough to see a sort of transformation. And that is 4 years ago, we required a computer science degree to get a job in the R&D department. That is no longer a requirement. We've sort of grown up, and so has the front-end engineering community. And it's no longer even necessary, I think, to even have a degree. I believe we've hired people without degrees, let alone computer science degrees. I'd say that right now about half of my friends and colleagues, they have computer science degrees and half don't. So when I introduced my talk title, UI Algorithms, I received a lot of questions, mainly from two camps of people. There were the computer science background people who had the algorithm part down, but really weren't sure what I meant by the UI portion of it. And then there were the non-computer science backend who had the UI part down, just not so much what an algorithm was. So today what I'm planning to do is help sort of blend these two camps and show you how we can achieve beautiful things in user interface land algorithmically. So we'll be diving into two algorithms today. One of them deals with optimizing hit state. That one actually involves a US presidential election and a cholera outbreak. Just stay with me. And the next one deals simply with menus. An alternate title for the talk was a complete disregard for rectangles. Since that is what we're going to be doing, we're going to be working around the HTML block level rectangular confines that were put in. That title ended up introducing more questions than it answered, so I'm sticking with UI algorithms. So to define an algorithm, we have the textbook definition here. It's a process or set of rules to be followed in calculations or other problem-solving operations. Basically, it takes an input, and then it will produce an output based on what the algorithm defines. If you're familiar with algorithms, these two books here should look pretty familiar to you. The one on the right is your basic textbook that would be in your college-level computer science algorithm course. The one on the left is more of an epic. That's Donald Knuth's The Art of Computer Programming. That's like a 4 or 5 series. It's all about algorithms, sorting, searching, and all that sort of algorithms. So let's establish a baseline for what I mean by algorithm. And here we have our first basic algorithm. This is not a UI algorithm. This is to sort of show you how I'm going to be using them. This algorithm just finds the largest number in a list. So we go ahead and we assume the very first item in the list is the largest. And then we iterate over every other item, and we check to see if the current item is larger than the largest. If it is, we save off the largest. This is something that we should all be able to write in JavaScript. This is something that might be asked on like a phone screen or something. It's a very basic, simple algorithm. So for UI algorithms, let's jump in, and it starts with these two guys. That's Mitt Romney and Barack Obama, obviously. And according to the New York Times, between the two of them, there were 512 paths to the White House. 512 should look suspicious, especially because we have our computer science hats on for the rest of this session. We know it's really 2 to the 9 paths to the White House. There's 2 ways a state could vote, Republican or Democrat, and there are 9 states in contention. And again, since it's a power of 2, it looks very clean in binary form. They decided to convey this information with a data visualization. And this is the one that they have here. Does anyone remember seeing this in 2012? It's cool, about like 25%, 30%. Already, just a screenshot of it, it does an amazing job of conveying the information at hand. It's using a binary tree to sort of represent the possible paths if a particular state were to vote Republican or Democrat. There was something in particular about this data viz that I saw on the night of the election, and that was there was a level of interaction. I'm sorry, the video is a little bit off, but there's a level of interaction. I think the only people that would really recognize this are people in this room and our colleagues, and that is, as I'm mousing over this viz, things are highlighting, the paths are highlighting, even though I'm not hovering over the interaction point. Those check marks aren't getting hit. I'm just in the general region, and it's knowing what it should highlight. It's highlighting the best possible thing for me. This had me very curious back in 2012 on how did they achieve this effect? Or rather, how would I achieve this effect? So what we're essentially doing is we want to increase the hit state of all of these elements. We have the elements are variably sized and variably placed, so it's not like they're all on a list. They're sort of random looking. So I thought the first algorithm that I would try would be variable size padding. If we want to increase the hit state, we can give something some inner padding, and that's something that we've all probably done before to account for mobile. The algorithm might look something like this. We go through each of the nodes in the list, and we set the node padding to the node radius times 5. Now, that node radius times 5, that's meant to be sort of arbitrary. What I was trying to go for is the bigger circles are up top. That should have a bigger hit state. So if it's 10 pixels in radius, it would have 50 pixels of padding. The smaller circles, 2 pixels in radius, would only have 10 pixels in padding. This could potentially work. I decided to draw this out on top of 512 Paths to the White House. It ends up looking something like this. So we do technically do one job of increasing the hit state. But we're also potentially introducing a bug, and that is if we're not careful with that node radius times 5 or whatever formula you use, we could start completely covering the hit state of our neighboring elements. And you could go back and you could tweak things, and you could go and add in some sort of z-indexing functionality to keep things on top of each other. But it gets a little bit hairy. I decided that's probably not what the New York Times did, so I moved on to another guess, which is to calculate the distance from the mouse position to the node position, basically to find the closest possible node to the mouse and then highlight that path. That algorithm would look something like this. On mouse move, we have an event. We grab the x and the y of that particular event. We go through each node in the list. We calculate the distance between the mouse position and the node position. And then we save off the smallest, and we would end up highlighting the smallest. This actually achieves the same effect that the New York Times did. So we did it with one particular exception, and that is there should be a lot of red flags raised in this room, because that is quite an event handler to have on mouse move. Even though this would technically work, we would be chugging the CPU, there would be noticeable lag, and the users would hate us. So I will say the algorithm is technically correct, but performance would be an issue. So what if, and this is sort of a big what if, but what if we can pre-compute the closest node to each possible mouse coordinate? So I'm talking about pre-computing every possible x, y coordinate to the closest node. That should sound crazy. That is crazy, given this visualization might be 960 pixels by 500. That's over 400,000 possible mouse coordinates that we'd have to go and compute and then save off somehow pre-hand. That's not going to work either, but what if there exists an algorithm that takes an input very similar to what the New York Times has, these variable sized and placed elements, and produces an output that is very similar to the algorithm that I just showed you? Luckily, such an algorithm exists for us. To show you that, first I need to introduce you all to a mathematical concept. This is called a Voronoi diagram. A Voronoi diagram is a mosaic. It's the dividing of this space into these regions, and it divides it in a very particular manner. And I want to jump in and show you the computer science definition of a Voronoi diagram. So it's the partitioning of a plane with n original points into convex polygons, each containing one original point, so that each coordinate within a polygon is closest to its enclosed original point than any other point. So what that means is we have this very dark pink purple on the left-hand side towards the bottom, one of the bigger polygons. Every pixel in that particular shape is closest to the black dot that's also in that shape than any other black dot. So to put that in more relevant terms, every possible mouse coordinate within that shape is closest to that particular dot. Another way to explain it, the non-computer science way, is that it partitions a plane around n original points while guaranteeing no overlapping and while maximizing the possible area around each point. So what we have here is a very simple Voronoi diagram. This is a 3-point Voronoi diagram. There's 1, 2, 3-point, and then more than 3. And there is an algorithm to generate these. There are 3 or 4 algorithms to generate these, but this one in particular is called Fortune's algorithm. This is a lot more complicated than anything I've shown you so far. This is not something I'm going to go through line by line, and this is not something, unless you have a PhD in computer science, that you're going to be able to understand in the amount of time that I actually keep this slide up. But what I will do is show you how this particular algorithm works. So the Fortune's algorithm generates Voronoi diagrams by discovering what's called a Voronoi vertex. And a Voronoi vertex requires 3 of the original points. So to put that visually, we've got the 3 original points, and then we have a Voronoi vertex in the middle. That's where all the lines meet. So Fortune's algorithm just works to discover these vertexes. And we can see that is the circle that the 3 original points live on the edge of. And in the center of that circle, we can put a Voronoi vertex. The circle needs to be empty. And I could show you in a video manner how this works. So this is how the algorithm works in very slow motion. So I'm going to pause it right there. What you're seeing are 2 big components of the Fortune's algorithm. The blue line moving from the top to the bottom, the straight line, that's called a sweep line. Its job is to discover these individual points. And the green line with that little parabola, that's called a beach line. And these 2 lines work in tandem together, discovering points and trying to identify these possible circles that it could put a vertex in the middle. So if we keep it going, we need 3 points for a vertex, so we'll see the algorithm actually draw a circle. We don't know if the circle is empty yet. The sweep line hasn't cleared the circle, so we can't put a vertex in there, but you'll see once it does clear, we go ahead and drop our vertex in. To show you a more complicated version of this, this has a bit more action. We've got a lot of circles coming up. The beach line is very active, and you can see right here, we've got this one big circle in the center. It kind of looks like Mickey Mouse right now. We put a circle there, but it's not empty. We can see that with our own eyes. The algorithm can't, because the sweep line can only look at what's behind it. So once we discover that circle's empty, that circle will be discarded, and new circles will be drawn, and it just keeps trying and trying until it can put a vertex in. Another cool one, because this is kind of just pretty to watch. This is probably 200 or 300 different points. This is very active. These videos and screen caps, if you Google Raymond Hill Voronoi, you've got this own, it's really cool, like you can click around and make your own original points and then watch the algorithm work very visually. So how does this apply to these 2 guys here? How does it apply to the New York Times? Well, luckily, what the New York Times had done was just write this in D3 with SVG, and we can use our inspector tools to sort of poke around. So by just adding a little bit of CSS to the page, we can see exactly what the New York Times did here. So I'm going and inspecting it. What we're doing is interacting with something that's currently invisible. It's got no fill and by default no stroke. So I'm giving it a stroke of 5 pixels, a stroke width of 5 pixels, and a black stroke. And then we can see exactly what the New York Times did. So they use the Voronoi diagram, and they're setting up just simple mouse enter and mouse exit handlers, which is a lot more performant than anything else that we saw. As you change the viz, we just recalculate the Voronoi once and set up the mouse enter and mouse exit handlers. So this approach is not just limited to a binary tree type data viz. You can use this in a lot of different types of data viz. So we have here, also in the New York Times, this is a scatter plot with some baseball players. I did the same exact thing. You go in with the Voronoi diagram, and you could show what's currently hidden. Here's a line graph that Mike Bostock posted. He's the creator of D3. And he posted, and there's even a little checkbox up here. This is just an example, and when you hit that checkbox, you can actually see what the Voronoi looks like when it's on top of it. So if you have like a hover over or some metadata you want to show about each of those individual points, something like this is a great way that you can increase the hit state of these items. So the algorithm, again, this is really complicated. This is not something I would recommend anyone really tries unless you're looking for a side project or an experiment. There are a couple of implementations for us, luckily. There's the D3 version, which is in the geometry package, and Paper.js ships with one, which is a cool physics-based JavaScript library. And when I was doing when I was figured out what the New York Times had done, I started doing a bunch of research about Voronoi, and it turns out it's got nothing to do with a user interface. They actually date back all the way to 1644. And they've got dozens of different usages. You can use it to figure out where to place a police station that's farthest away from the other police stations. They can be used to determine capacities of wireless networks. They're used in robot navigation, too. If the original points of those black dots are obstacles, then the edges of the polygon are farthest away from all of the obstacles, so you can route yourself safely. It's only recently with HTML, SVG, and Canvas can we actually use those for user interface. Some more of the history, which I just found this awesome story that I have to share with you all. It's one of the first notable uses of Voronoi happened in 1854, which is 60 years before Voronoi put his name on it, but it was still a thing back then. And who used it is the guy to the right, who was a physician named John Snow. That's his photograph. I was able to dig up a higher res version of his photograph. I had a Microsoft Bing joke in there, but they sponsored the event, so I felt really bad burning them on that one, so I'll skip it. In 1854, there was a cholera outbreak, and there's a lot of cholera outbreaks in London. In particular, there's an outbreak in Soho that was hit really hard. Over 600 people had died before the source was discovered. So John Snow was very familiar with the neighborhood, so he decided to plot the deaths out on a map. And this is John Snow's actual map of Soho, and you can see the deaths are these black tick marks coming out of each of the residences. After plotting the deaths, he plotted the public water pumps. This is 1854, so indoor plumbing isn't really too much of a thing in downtown London. The water pumps are going to be the original points of the Voronoi. So there are some of the water pumps. They're little black dots with the word pump written on it, but you can't see it unless it's zoomed in. So there are some arrows. After seeing this data, John Snow actually already had this theory, but this helped prove his theory that the cholera outbreak was happening from a water pump, from one particular water pump, the Broad Street pump. And this is with some modern-day visual aid, sort of what he was seeing. So we've got the Voronoi diagram. Soho is split up based on the water pumps, and there are more than a majority of the deaths are happening in one of those particular shapes. And in the center of that shape is the Broad Street pump. So, crisis solved, except for the fact this is 1854. So the idea that disease was spread through water was still not accepted. It was very controversial. Louis Pasteur doesn't come up with a germ theory for another 10 years. And the popular theory at the time was called the miasma theory. And it was that disease was spread through a noxious cloud that would just sort of fumigate around houses and people would get sick. The evidence that you saw was pretty damning, though. They still went and removed the handle of the pump, and the deaths stopped in Soho. And they investigated. It turns out a cesspit was dug too close to the water pump, so he was absolutely correct. So even though he helped stop the outbreak, he was actually still ridiculed for his theory. He still wasn't accepted by all of the science community. They actually dismissed the theory that disease could be spread through our waste as too depressing. That's a real quote. The officials at the time likely said something along the lines of, you know nothing, John Snow. That's not a real quote. And then we all know the rest of his history. He was later banished to Castle Black and swore an oath to the Night's Watch. What actually happened to him is really too depressing. He ends up dying only 4 years later, and he's never actually fully vindicated. He never actually gets his theory proven and accepted by the science community. However, if you go to where that water pump was, there's now an intersection in Soho, and you can stop into the John Snow Public House and have a pint. They named a pub on that corner after him. So I'm done with algorithm number 1, and I am unfortunately out of Game of Thrones jokes. But so we'll move on. Honest mistake, I forgot about that slide. Also, I broke the ice on the first meme slide for JSConf, so all the other presenters, you're welcome. You can go ahead and use these things. Algorithm number 2. This one deals with hierarchical menus. And to show you the problem at hand, I'll show you the submenus from Bootstrap 2.3. And that is, as I move my mouse directly to the call to action, it's disappearing on us. This is frustrating. You have to move it perfectly horizontal. In the same vein, if I clip the menu item above or below me, it will also disappear. It will fire that mouse enter and not listen to what I want. So it's the only way to get to that call to action is to move your mouse perfectly horizontal, which is annoying. So the menu will hide when it hits the corner of another menu item or when you mouse over some empty space. If you've ever studied HCI, human-computer interaction, you probably recognize the name of Bruce Tognazzini, also called the TOG. The TOG had something to say about this. He says the engineer who originally designed hierarchicals apparently had his forearm mounted on a track so that he could move it perfectly in a horizontal direction without any vertical component. It's not the nicest thing he's ever said, but luckily we have a solution for this that a lot of us have probably implemented at some point, the set timeout trick. So that particular algorithm might look something like this. So on a menu item mouse enter, we clear all the timeouts if there were any. We go ahead and we save off the currently selected item, and the currently moused over item rather. We set a timeout for something around 150 milliseconds, maybe shorter, maybe longer. And if that timeout hasn't yet been cleared, then we go ahead and select that particular item. So here is an implementation of that algorithm. So we can see we've solved the original problem is I can move diagonally, even though I'm clipping the menu item below me, it's still giving me time to get to where I want to go, which is cool. However, we've also introduced a noticeable lag in the way this thing disappears. It has to stay around for whatever timeout that we had, or else the algorithm doesn't work. So we solved one issue, but we introduced this annoying lag. Here is another example of these menus. This is Amazon's example, and you can see Amazon, there's no lag moving up and down, it's working great. And I can also move diagonally and clip the menu items above or below me, and it will still respect what I want to do. It's basically predicting exactly what I want to do and not getting in my way. So Amazon was able to have both of these, or not have a single one of those problems and just have an optimal menu system. So what we need is an algorithm that doesn't interfere with the blue path and moving up and down, and only helps with the red path of moving towards the call to action. Luckily, last year, Ben Kamens from the Khan Academy, he wrote a blog post called Breaking Down Amazon's Mega Dropdown, which is something I highly recommend people checking out. He outlines the same exact problems that I just showed you, and then also outlines Amazon's really nice solution. The algorithm to achieve this would look something like this. So we start off with our slope function. We all know slope from grade school, that's rise over run. And then we calculate, in the actual mouse event, we calculate the upper right and the lower right bounds of the box. And then we start tracking the slope. So what I'm doing here, and I'll show you a visual of this, but we're tracking the increasing slope from the mouse pointer to the upper right and from the mouse pointer to the bottom right. And what we're doing is we want to check to see if the slope is increasing or decreasing over time. So if we're moving towards the right, so if the decreasing slope is less than the previous decreasing slope and the increasing slope is greater than the previous increasing slope, then we just set a timeout for 10 milliseconds and give them more time to make their way to the menu, because we can safely deduce that the mouse is moving to the right. And to show you what I mean by safely moving to the right, here we have our basic XY grid. We've got 1 point up there, 10, 10, and then 10, negative 10. We can go ahead and assume that this is the upper right and the lower right bounds of the menu box. We have the mouse cursor right there in red. We have the lines that go from each one of those. What we want to do is calculate the slope of these particular lines. And in this case, it would look something like the slope of the line going down is going to be negative, so it's negative 1.87. The slope of the line going up is going to be positive. And as the mouse moves, we check again, maybe in 10 milliseconds, to see how far they made it. And we want to calculate the slope again. So here we have the slope is 4. The line is getting more and more steep. So as it nears towards perfectly vertical, you're nearing towards sort of infinity. So as long as that number is increasing on the increasing slope, and as long as it's decreasing on the decreasing slope, we can safely guess that the mouse is moving towards the right. So if the first dot with the slope of 0.625 and 187 is the previous event in this algorithm, the second dot is the current event. So here, again, we have the previous event with the previous slope and the increasing slope. And this algorithm works. You can conceptualize it by, this was included in Ben Kamens' blog post. This is sort of, this is an invisible triangle that's added over, and any mouse movement that's towards the right that stays within the bounds of this triangle will keep the menu open for a little bit longer. If the mouse is moving perfectly down or left or up, then we go ahead and we go to the default behavior without any noticeable lag. So we have another quote from Tognazzini. He says that when I specified the Mac hierarchical menu algorithm, I called for a buffer zone shaped like a triangle so that users could make an increasingly greater error as they neared the hierarchical without fear of jumping to an unwanted menu. As long as the user's pointer was moving a few pixels over, for every one down, on average, the menu stayed open. And again, a buffer zone shaped like a triangle. The algorithm that I summed up for you lives in a project called jQuery Menu Aim, which is also written by Ben Kamens and introduced in that Breaking Down the Amazon's Mega Dropdown blog. The algorithm itself in JavaScript is probably around like 40 lines of code with copious amounts of white space and comments, so it's something that you can consume really easily if you want to go and read it. The comment section of that particular blog post, the Breaking Down Amazon's Mega Dropdown, was very interesting. We have a comment started by Jake Smith here who says, this was first implemented by Apple's HID team back in the 80s, specifically Bruce Tognazini, I believe. This guy is everywhere, literally everywhere. He even comments on this blog post himself. He says, yes, I did invent it back in 1986, and it is firmly in the public domain. From what I remember, it was Jim Botson who worked out the math and coded it for Mac OS. I want to stop there because this is kind of important. This is 1986 that this was a problem, and this was solved in 1986. And it's only recently that we're like, hey, Amazon, fix this. That's great. If it's 1986, it's very likely that this was somewhere in the development cycle on the day that I was born. And now I'm up at JSConf like saying, hey, use this algorithm. Whenever we, as user interface developers, want to recreate an existing user interface that might be provided by an operating system, we open ourselves up to forgetting about these very important parts, these usability issues here, and we cause bugs like this that have to get solved way after HTML and JavaScript were invented. So the the Tog goes on. I can't call him the Tog. I feel like he's Bruce. The OSX team later failed to copy the algorithm, so I'm happy to see that Amazon has resurrected it. And it's important to note in Mountain Lion and in Mavericks, that algorithm is actually back. I think it came in an update in Mountain Lion. If not, then it just might not have been on his computer at the time. And Amazon has resurrected it, so where would a comment section be without a troll? Hey, Apple, time to sue, because they sue people who copy from them. So that's all I've got. Thank you.